In this video, we're going to look at solving rational inequalities, and we're going to continue the theme of solving inequalities much like equations, and then set up a number line and using test values. However, in addition to the answers we get from treating the inequality like an equation, so how we would solve it like we did in the previous videos, we're also going to have to consider the values outside of the domain. In other words, where the denominator equals 0 on our number line. So our critical values on our number line are going to be not only the solutions that we get to the equation, but also the values that would cause the denominator to equal 0. So example 2, solve each of the following and graph your solution on a number line. So we have 1 over 5x is less than 1 over 5x squared minus x plus 5 over x squared. So we actually solved this equation in the previous couple videos. So from example 1a, in fact the first video, we got x equals -4 as the solution to the equation, and x not equal to 0 because it would cause the denominator to equal 0. So those are going to be our two values on our number line. Now because it is a less than symbol, if we plug in -4, we would get the left and right sides to be equal. We would need the left to be less than the right, so this is an open circle at -4. 0, because we do not ever want that denominator to equal 0. The values that would cause the denominator to equal 0 are automatically open circles. So please keep that in mind, that the solutions to the equations are based on the inequality sign and whether it has that equal to part, but the ones that cause the denominator to equal 0 are automatically open circles. So now if we test out a value that's less than -4 in the original inequality, we can then test out a value between -4 and 0 in the original inequality, and then test out a value greater than 0 in the original inequality. We'll see that values less than -4 will work, and that's it. So our only values that work in this original inequality are values less than -4. Part B, 5/3 minus 1 over x is greater than or equal to 1 over 3x. So we could treat it like an equation, and we solved this equation in example 1b. So for the equation solution, we got x equals 4/5, and we said that x could not equal 0 because we didn't want a 0 in our denominator. So setting up our number line, 0 is automatically an open circle because we don't want the denominator to equal 0. But 4/5, because it's the equal to in the original inequality, 4/5 gets a closed circle. And then if we test out a value less than 0, it'll make the original inequality true. If we test out a value between 0 and 4/5, like maybe 1/2, it will not make the original inequality true. And then any number larger than 4/5 will make the original inequality true. So we have x is less than 0 or x is greater than or equal to 4/5. Part C, we have 1 over x plus 4 less than or equal to 6x minus 42 over x squared plus 4x plus x over 8, or x minus 8 rather, all over x squared plus 4x. So treat it like an equation, and this goes back to example 1c. We got x equals 25/3 as the solution to the equation. And then for our values of x that we were not allowed to have were 0 and -4. So setting up our number line, the -4 and 0 automatically get open circles because we don't want those denominators to equal 0. The 25/3 will be a closed circle because of the equal to part in this inequality symbol. So 25/3 will cause the left and right sides to actually be equal, so it's okay to have it. And then testing out values, we have 1, 2, 3, 4 different sections on the number line we got to pick a value from, and we find that a value between -4 and 0, such as -2, and a value larger than 25/3, such as 10, will make the original inequality true. So our final answer for example 2c are values of x that are between -4 and 0, so x is greater than -4 and less than 0, or values of x that are greater than or equal to 25/3. All right, that about does it for this video. Thanks for watching, and I'll see you next time.